Okay, so this is Cog Neuro lecture number 3 for midterm 2. And the first thing we're going to look at is a neglect syndrome. And so neglect syndrome isn't what it sounds like. It's more of your brain has a bias towards one side of your vision field. And it's also called hemispatial neglect. And so essentially what you're doing is you're neglecting the left side of your vision field. And so you're only looking at the right side, which is easy to remember. Like you're looking at the right side, like that's correct. Right, correct, you're looking at that side. Um, and this can refer to what you're seeing in front of you, so you only see the right side of what you're looking at, and also even to things in your mind. Like if you're trying to visualize a clock, you'll probably only visualize the right side of that clock, and all the numbers will be crammed on that side, and there won't be anything on the left side. Whereas and also if you're like drawing a house or something, you might only draw the right house of the right side of the house with like all the windows on the right side and the chimney on the right side. You won't be able to copy down the left side of the house, even if it's just in your head. And then another thing is if you bisect the line, you'll bisect it basically in the middle of your right field of view. And so you'll basically bisect it 3/4 all the way down because you're only seeing the right side of that one line. Okay, and so basically how you acquire this neglect syndrome is that you get some kind of lesion. And so often it's the right inferior parietal cortex. And so you can think of that as RIP-C, right inferior parietal cortex. And so RIP-C lesions are usually a result of the stroke, and it's usually because this has affected something in the right middle posterior cerebral arteries, the right middle or the posterior cerebral arteries. And so basically the RIP-C, which is right inferior parietal cortex lesion, is due to stroke, and this is because it affects some artery going down the middle. And so another thing based on what this neglect thing is essentially what it is basically the objects in your right field of view are winning the competition for attentional resources, because as you remember, there's only a limited amount of attention that you can spend on any one thing. And so basically what this is that the right side of your attention is winning the competition. And a lot of people view this neglect syndrome as a disconnection syndrome, and they think that this disconnection syndrome is kind of disrupting the right side of the spatial attention network. And so they think that there's a spatial attention network that works for, and there's one on either side, and one network is working to modulate the right side, one is on the left side, and basically this syndrome is a result of these two things being disconnected. And so getting a little bit more into that, someone named Mesulam, so Mesulam, you can remember it because he's messy, and this is a pretty messy kind of topic, and I assume that if you had this, you probably would have one side of your room that was really messy because you could only pay attention to one side of kind of spatial objects or something like that. I'm sure that's not accurate, but Mesulam. And he thought that this network consisted of basically a couple different brain regions. And so I'm going to list them off, and you can kind of remember them all because they all kind of relate to eyes in some way. And so he was thinking that the spatial attention network consisted of, first, the bilateral frontal eye field. And so that's basically just the FEF. And so that's the frontal eye field. And so that has to do with eyes. And then also he thought that another thing that was in the spatial attention network was the posterior parietal cortex. And you can think of this because there's two P's in this, like posterior parietal, and you can kind of think of this as your two eyes. And then the next thing is cingulate gyrus, which is super weird. You can kind of think of gyruses if you remember those toys. They're kind of little circles, and cingulate gyrus. And so just kind of think of a circle gyrus, and that there's two of them, and they're kind of like your eyes. And so going back, it's bifrontal FEF, posterior parietal cortex. So it's FEF, PPC, and cingulate gyrus, and also, it's the subcortical nodes of the thalamus. And so these subcortical nodes, you can kind of think of these nodes as eyes also. And also superior colliculus and striatum. And so that's a lot of things. And so just going back, it would be bifrontal FEF, PPC, which is postparietal cortex, cingulate gyrus, which is like gyrus for two eyes, and subcortical nodes in the thalamus, which also sound like eyes, and superior colliculus and striatum. And so that's quite a thing to remember. Just remember the two that kind of don't sound like eyes are the superior colliculus and striatum. But you can just think of this SCS because superior colliculus, that's one, and then S would be striatum. And so now that we're done with that, basically, the thing with all these things is that they are all kind of innervated, or like this one thing goes through all of them, and that's the ascending reticular activation system. And so ascending reticular activation system, and so that's ARAS, so we can think of it as ARAS. And so basically like all of these little eye sounding brain regions, which were discovered by Muselium, whose room was probably really messy, are kind of all innervated by this ARAS, or ascending reticular activation system. And that makes sense because ascending means that it would kind of be going up, and that would make sense because it's probably going up from your eyes. And then reticular activation system, that would make sense. And so all of these different things discovered by Mosellam were innervated by the ascending reticular activation system. And then another thing to know about this is that this ascending reticular activation system, because it's kind of going up, it is in the brainstem. And so all of these, the spatial attention network is all innervated by ascending reticular activation system of the brainstem. Okay, and then And so basically what you can divulge from all of this is that if you have this kind of neglect syndrome, it's probably because your PPC and FEF nodes are separated. And so basically the PPC and FEF are usually connected, and this kind of neglect syndrome would be because they're disconnected. And so PPC, FEF aren't friends. That leads to a neglect syndrome discovered by Mesulam. Okay, and so now we know what it is, and we know that it's caused by a lesion, but then we're wondering now why it's only on one side. Like, how come we don't see people that can only focus on their left side of attention? How come it's only people that can only focus on their right and have to ignore their left? Why is it never the reverse? And so there's two models to back this up, and the first one is the representational model. And so basically what that says is that you have two sides of your brain and two of these attentional spatial control systems. In the right side attends to both contralateral and ipsilateral space. And so that means that contralateral means the right side attends to the right and left visual field, but then the left side only attends to contralateral. And so basically what this would mean is right side of your brain is looking at both directions of field of vision. Left side is only looking at your right. And so that's why if you get this because of a lesion in your right brain, that's only going to destroy your right brain, which is looking at both sides, and then you're only going to have your left brain, which only looks at the right side. And so it's basically you just need to draw a little picture and show that the right side of your brain is looking at both fields of vision, the left side of your brain is crossing over and only looking at the right side. And so then this explains why if the left side is damaged, then you're only destroying your contralateral thing, and so then you're destroying one powerful effect to look at the right side, but you're still going to have the right side of your brain, which is looking at both sides. Okay, and so the first one was called the representational model, and that can make sense because it's basically like pretty basic, just that the right side looks at both sides of your vision field, the left side only looks at the right side. And so the second model is the attentional bias model. And you can think about this one because it's a little bit more complicated because there's a bias, and then this one also has to do with inhibition. And so you can think about that like the first one is just representational. They both just have their directions that they look at. The right side has two, and then this one has to do with biases and inhibitions. And so basically this theory starts off that both the left and the right side both attend to contralateral spaces only. And so basically they're saying the right side of the brain only looks at the left side of the visual field. The left side of the brain only looks at the right visual field. And so it's kind of like a little crossover X thing. Right looks at left looks at right. But then they're saying that the left side is kind of stronger, and so the left side of your brain is stronger, and so it has a stronger contralateral bias. And so basically, like the amount of power put into the left side is higher, and so that means the amount of power looking at the right visual field, because it's a crossover, is going to be higher. And so left side stronger looking at the right field of view. And then the other component to this is that the two sides inhibit each other, and so then this is important because then if the right side of the network is damaged, then what's going to happen is the right side of this network basically inhibits the right brain of this network inhibits the left side, and then what you're basically no longer inhibiting because the right side is damaged is the leftward bias and the inhibitory function of the right side are lost. And so basically, because the right side is damaged, it doesn't inhibit the super strong left side anymore, and so the left side, which was already super biased looking at the right side of vision, is now going to be even more strongly looking at the right side of vision. And so then this goes that also, if you damage the left side of your brain, it's not going to be as bad because basically, what do you call it? And if you damage the left side of your brain because the left side has so much like power towards the looking at the right field, and it's like much stronger than the right side. If you damage the left side, it's not going to be as bad of a bias. But yeah, and so basically this can be summarized up as two sides of the brain. They both only look at the contralateral, so right, left, right, and they both inhibit each other, but the left is much stronger, so there's a bigger bias towards the right field of vision. Okay, and so now we're looking at the difference between we're kind of looking at the experiments with the cues and then the targets. And so basically like the cue says, oh, the target that you're looking for, which is maybe a red box, is probably going to be on the right side of the screen. And so basically the difference between a cue period and a target period is that people think of the cue period as purely a top-down attention thing. I think it's pure top-down attention. So it's pure brain sending signals to your eyes, looking for something specific. Cue is pure top-down, whereas the target period, which is when you're looking for something specific and when you see that little red box that you're supposed to, and that's a mix of processes which include target detection and response selection. And so it's pretty hard to distinguish these two things because they overlap temporally so much. And so fMRIs usually use a long jittery cue period, which I don't really know what that means, but think of long jittery cue period because it's hard to sort out cue from target period. Okay, and so then another thing to know is that the FEF and the PPC are thought to be really important for top-down attentional orienting. And so FEF, PPC you need for this special cue period where you're looking for something specific. And the cue period is also defined as the period that is more directed by neural cues, which again is that top-down idea. It's going from your brain and sending signals to what specifically you're supposed to be looking at. And so, yeah, FEF, PPC is the cue period because it's top-down. Your brain is sending signals to your eyes on what to look for. Okay, and so then another thing to know, which is a bit unrelated, is that attending to space and attending to stimulus features kind of recruits the same brain regions. And so basically, like if you're looking around at a room, whereas if you're looking at like what color the walls of that room are, that's a space that's analyzing space when you're looking around the room, and then analyzing a stimulus feature, which is the color of the walls. Those recruit kind of similar regions in the brain, and so that's saying that these are probably like shared resources, and these regions that it recruits are the frontal and parietal regions. And so if you're looking at space versus feature, it's probably going to be overlapping similar regions. And then another thing to know about that is that if we want to disentangle kind of the cue and the target relationship, we should use EEG because it's good for temporal stuff. And so when you use EEG in combination with the fMRI, it kind of gives you data that suggests that more lateral, frontal, and parietal cortices are involved in general cue processing, and more medial regions are involved in spatial orienting properties. Okay, and so basically to go over that again, the lateral, frontal, and the parietal cortices are more involved in general cue kind of stuff, and then the more medial regions are for spatial orienting. Okay, so lateral, frontal, and parietal cortices, general cue, and medial regions have to do more with spatial orienting properties and stuff. And so you can think of that because the medial region, you can kind of think of that as a piece of meat that you need in the center of a room and you need to orient it properly spatially. And so medial regions have to do with spatial orienting properties, and lateral, frontal, and parietal cortices have to do with general cue processing and stuff like that. And then another thing to know is the order of things as they go down. And so EEG analysis, because EEG, again, is really good at temporal stuff. And you can remember this because EEG kind of looks like the word egg, and eggs are very temporally oriented in their development. Like there's a certain day when an egg is going to hatch, and there's a certain day when an egg is going to have a certain developmental stage of fetus inside of it. And so the EEG analysis of these kind of cue experiments shows that the frontal or the FEF portion activates before the parietal component. And so basically what you need to know is that in the sequence of events, frontal brain region activates first, then parietal. So FEF and then parietal. Okay. Okay, and also because of this kind of frontal goes first and then parietal activates, people think that this is kind of a representation of a salience map. And so like frontal and then parietal, and this is helping with the salience map. And then again, the salience map kind of helps you guide what you're searching for and what you're looking for, and so that you find the correct stimulus that you are searching for in a cue target kind of experiment. And so basically another thing that you need to know about this is even before you're shown the cue or anything like that, if you're told what you're looking for, you can kind of see a baseline activity shift in your brain, and this is like an anticipatory thing. And so this baseline shift is going to enhance the responsiveness of certain regions to the target stimulus. And so basically, like if the experimenter tells you, oh yeah, you're going to be looking for a turquoise box, you'll kind of sensitize those regions with a baseline activity shift, and you'll be more sensitive to detecting these kind of things. And so inside the PPC, there's a lateral intraparietal area. So lateral intraparietal area inside the PPC. So that's the LIP inside the PPC, and so that's the lip inside the PPC. And basically what these neurons do is they enhance their firing rate when attention is directed to their receptive fields. And so basically if you focus your attention on something that is going to lead back to them, their firing rate enhances. And these, both of these regions are involved in the planning and execution of saccades, which are basically eye movements. And so this all leads back to the attention and eye movement relation. So people think that paying attention to something and eye movements are related, and that is called the premotor theory of attention. So premotor theory of attention basically means that even before you mobilize something like saccades or something, attention is going to influence the way that that happens. And another thing to know, which is done by Moore, just like by neighbors, so Moore, the causal role of the FEF in a top-down biasing of visual processing. So basically what that means is that the FEF, essentially, the FEF might be where attention kind of originates, sort of, because there was an experiment, and so they microstimulated FEF neurons, and then they recorded from the V4 neurons that these FEF neurons were going to lead back to, and then if you stimulate the FEF neurons, basically it produces an enhanced and even stronger response in these V4 neurons that it leads back to, just like it does in attention that we talked about earlier. And so basically this mimics the effects of attention. And so to review the FEF, if you stimulate it, it kind of causes the V4 neurons that it leads back to fire even more, mimicking attention. So FEF, stimulation of FEF can kind of mimic attention. Okay, and then one of the most important things to know about those previous saccade things is that the simulations that they did in the FEF were sub-threshold, so they weren't enough to trigger a saccade, but they were sub-threshold FEF simulations, so that's important. And then another thing to know about these sub-threshold FEF simulations is that they enhance sensory discrimination. And so basically what that means is that it'll be easier for you to detect something like a light dimming if you have one of these sub-threshold FEF simulations. And so again, this is mimicking the effects of endogenous attention. So this is attention coming from within that you're kind of modulating. So you're thinking up what you want to attend to, and then you're doing that. And then this is mimicked by FEF sub-threshold simulations, which don't quite induce a saccade. Yeah. Okay. And so then basically this all leads back to the difference between covert and overt shifts of attention. So overt are kind of like physical, real shifts of attention. So that would be saccades, your eyes moving, physically moving to a different piece of the world to focus on that. And then covert shifts of attention is just kind of like thinking like, oh hey, I should probably pay more attention to what the professor is saying rather than looking at this cute dog online or something like that. And even though they do show a lot of overlap, they are not entirely the same. And so basically you can divulge this because of the differences in different FEF neurons. And so some FEF neurons are basically only involved in saccade orienting, and so they're active during gaze shift. So basically some FEF neurons turn on when you're kind of moving your little eyes around the room, like looking around, and so that would be overt attention. But then some FEF neurons are only active when you are kind of, they're signaling the location of behaviorally relevant visual stimuli. So basically like you're thinking about like, oh, what should I look at? Like maybe I should look over to the right. And so it's basically selecting possible saccade targets without being actually involved in producing these saccades. And so basically some FEF neurons produce the saccades physically, which is the shift in gaze, but then some FEF neurons also are just thinking about like, hey, where should I look next? Where should I tell these saccade neurons to go next? And so that is showing that covert and overt shifts of attention are not identical.